Alright, in the next two videos I'm going to go through two different worksheets, but I'm going to talk about differentiability, meaning can you take the derivative or does the derivative exist, and the relationship between differentiability and continuity. So remember, continuity means there's no holes, breaks, jumps, vertical asymptotes, or anything like that. Differentiability means the slope from the left is going to the slope from the right. So let me give you an idea by that. If I come in, and here I have a nice little quadratic, and here is my point. If I'm talking about a slope coming in from the left, and a slope coming in from the right, and are my slopes equal, or are they kind of weird looking? I'm going to show you what I mean by weird looking in the next video. But essentially, what we're talking about is the slopes are the slopes actually the same on both sides of this specific point. So if a function is differentiable at a point, then it has to be continuous at that point. So differentiability and continuity have to go hand in hand. However, you can have it be continuous at a point and not differentiable at a point. And we'll talk more detail next time at the next video, but we're talking about cusps, corners, vertical tangents. Again, if anything that's discontinuous, there's no way it can be differentiable. So let's go through several examples. Number one, let f be a function such that the limit as h is going to 0 of f of 2 plus h minus f of 2 divided by h is equal to 5. Now in our last video we talked about this is essentially the definition of derivative at a specific point. In this case my point is 2. X is equal to 2. So we have a derivative. My slope of the tangent line at x equals 2 is 5. So that's my m. So I have a derivative. So which of the following has to be true? Well, if I have a derivative, it has to be continuous. Differentiability, if differentiability is true, then continuous is true. So number one is correct. Is f continuous at 2? Yes. If it's differentiable, it has to be continuous. Because I have a derivative and it's equal to 5, 5 is an actual value, it's an m, I can be located there. It's not DNE or undefined. Number 2 is also true. F is differentiable at 2. Yes, it is, because I've been given an actual value. Number 3, the derivative of f is continuous at x equals 2. My limit formula, never really discusses continuity of the derivative. It just only talks about does the derivative exist. And so I cannot for sure say if 3 is true or not. Most likely it is, but I can't, with the information that was given, I cannot prove that. So at this point, only I can say is C, 1 and 2 are true. Alright, number 2, let f be a function defined by f of x is equal to 2x minus x squared, where x is less than or equal to 1, x squared plus x kx plus p, where x is greater than 1, and the derivative of f prime of x is equal to 2 minus 2x, where x is less than or equal to 1, and 2x plus k, where x is greater than 1. Typically, I'm not going to give you that f prime of x. You're going to have to figure that out on your own. But since I haven't shown you any of the shortcuts yet, I'm just going to go ahead and give it to you, and I'll come back later and probably on multiple choice Monday or free response Friday and have you practice without the f prime of x. But at this point, I'm just going to go ahead and give it to you so you get the idea of what we're doing. Alright, we are assuming continuity and differentiability. And so we're trying to solve for two unknowns, k and p. Well, since my derivative has one of those unknowns deleted, I don't have to worry about that p. I'm going to go ahead and solve for k. I want to find what that value is. And specifically, I'm checking in that troubled spot, which happens to be where x is equal to 1. And so if it's differentiable, that means that my left-hand side, my left-handed derivative, has to equal my right-handed derivative. So my left-handed slope has to equal the right-handed slope, specifically at 1. So if I plug in 1 into the left-handed side, I'm going to get 2 minus 2 times 1 is equal to 2 times 1 plus k. And if I was going to solve, let's go ahead and solve for k. That means 2 minus 2 is equal to 0. And 2 plus k, that means k has got to be negative 2. So we know what k is. Now let's go ahead and try to find what p is. Again, we're assuming continuity. That means my 2x minus x squared has to equal x squared plus kx plus p. So I'm going to go ahead and plug in 1. So I have 2 times 1 minus 1 squared. And that is equal to 1 squared plus, in this case, we know what k is. K is negative 2. So we have negative 2 times 1 plus p. And so let's go ahead and simplify. So I have 2 times 1, which is, or 2 times 1 minus 1, which is 1. And then I have 1 squared minus negative 2, which is negative 1 plus p. If I solve for p, I'm going to get p is equal to 2. Alright, number 3, prove whether g is differentiable or not. And so we have g of x is equal to x squared plus 4, where x is less than 1. And 3x plus 2, where x is greater than or equal to 1. And again, I just went ahead and gave you g prime. Typically, I'm not going to, after I show you the rules, I'm not going to give that to you. You're going to figure out that on your own. I have 2x, where x is less than 1, and 3, where x is greater than or equal to 1. So, let's go ahead and make sure it's continuous. So if it's continuous, that means my left and my right are going to be equal to each other. So if I plug in 1 into the left-hand side and right-hand side, my limit should be the same. So we have the limit as x is approaching 1 from the left. Again, this is the left-handed side. This is the right-hand side of x squared plus 4. That should equal the limit as x approaches 1 from the right of 3x plus 2. And if you notice, if I plug in, this is going to be the left-hand side, it's going to be 5. If I plug in 1 on the right-hand side, it's going to also be 5. So in terms of continuity, we're good. Well, now let's check differentiability. And differentiability, again, this is the left-hand side, this is the right-hand side. And so these are our derivatives. Are our slopes coming up the same side? Are they equal to each other? And so I want to check, does the limit as x approaches 1 from the left of g prime, which I'm going to go ahead and write 2x, does that equal the limit as x approaches 1 from the right of, again, g prime of x? So if I plug in, I'm going to get 2 on the left-hand side. I'm going to get 3 on the right-hand side. And so although it's continuous, it's not differentiable. My two slopes are not equal to each other. I have a slope of 2 on the left-hand side and a slope of 3 on the right-hand side. And so it looks like my function is coming to a corner where my slopes are not going to be nice. I probably have something that looks like this. It's coming up and then it cuts off. This right here is at a corner where my slopes are just not working the way they're supposed to. And so in this case, my function is not differentiable. So, whoops, not differentiable. Finally, number 4, using the graph below, determine if the function h is differentiable at the point x equals a. So let's look in. And we're talking about a. Here's my a. And we want to check, do the slopes. So you can see it's continuous. There's no holes or breaks right here. But I want to check, does the slope from the left equal the slope from the right? Well, if you notice, what's the slope this way? I hope you get 0. What's the slope this way? Again, I hope you get 0. And so, is a function differentiable at the point x equals a? Yes. Yes, it is. It's continuous, which we've already talked about, and it's also differentiable. My f prime of a is equal to 0. And so what we're going to, after this, what I want you to do is go ahead and watch the next one, and we're going to really talk about, specifically graphically, where differentiability breaks down.